Welcome back. In this video, we would like to examine specifically the variability, the fluctuations that ultimately lead to the generation of waste. We have discussed and covered in the earlier video sessions about how variability constitutes one kind of waste, fluctuations, right? So this aspect of waste is again invisible, right? When things change, fluctuate, or occur in an unexpected fashion, to businesses, it becomes a very short-term reactionary event, what we normally might say firefighting mode, right? So that, of course, means a lot of disruptions, a lot of last-minute arrangements, a lot of time compressed decision making, and inevitably there will be mistakes, there will be high costs, there will be um, redundancies, and thereby generating a lot of waste, right? So, and then of course, it is a short-term thing, right? So when the fluctuation or the variability somewhat, is treated or gone for a moment, then what happens to all the last-minute arrangements? They will have to be dismantled, dismissed, right? Temporary workers dismissed, temporary rental sites, uh, uh, discharged, um, and so on. Then you can see why it will lead to high costs, redundant costs, and waste ultimately. Right. So we have just three points to look at: the queue process. So we do have a queuing theory that already has been very well studied, I would say, to look at various kinds of queues, but we'll look at just a simple queue setup in order to understand how theoretically we treat variability. Then there is this time in queue that deserves a little bit of a mention because it's a formula, right? And formulas are good because the formulas give us predictability. So long as you plug in the various numbers into the right hand side variables, you perform the mathematical operations, you get the left hand side required quantity, such as time and Q. And finally, all these lead to fluctuations, lead to waste, lead to undesired um, additional costs to the business. And so recognizing them will be very valuable. Even if we cannot totally eliminate them, at least we recognize what are the sources, where to look out for, and to ameliorate the situation as much as we can. So, very first question, why do queues form? We cut to the chase. Why queues form? Why queues form? Now, a layman might just, in a way, mistakenly think of it as when there's rapid arrival of customers, right? And you are, incapable of serving fast enough, then queues will fall, right? Or there's rapid arrival of customers and you can serve them, but somewhat, you know, inconsistently, then queues form, yes. But that usually is all tied to when rapid arrival of customers, right? In other words, if we talk about FR in and FR out, if you recall, right, FR in, the flow rate into the process, and the flow rate out from the process. So one normally associates the reason why a queue form is that FR in is high. But here we're going to, totally refute that. We're going to say, no, queues form, right, because of fluctuations in two sources. The inter-arrival times, we call it the A instantaneous, that means moment to moment. If you measure the inter-arrival times in real time, right, and where it moves up and down, right, fluctuations, right, that's the A instantaneous. Or the fluctuations, the changes, the variability in the instantaneous service times, we put it as P underscore instantaneous. That means if you again measure the time it takes to serve or to process, the P is the same processing time as what we learned in the process analysis earlier on. So the processing time. Okay, so the processing time per flow unit, if we measure that, and remember in a high performance factory, you are generating millions of units every day, right? So there'll be a lot of processing times, and if we record them and note them in a time series or a histogram, better still, then you find that the fluctuations, right? If there's fluctuations, it will lead to the formation of queues. Okay, so first thing first, queues form only due to these two reasons. So another way to put or describe mathematically the fluctuations is that the standard deviation of A instantaneous, so sigma A, is not zero, right? We all know, right? Standard deviation, the larger it is, the bigger, yeah, the swing of the curve, right? And in this case, the curve describes, as time passes, the instantaneous, the moment by moment, real time measurement of the inter-arrival times. Okay, or standard deviation of P instantaneous, represented by sigma P, whenever it is greater than zero, or not zero means greater than zero. The larger standard deviation, the larger the fluctuation. The smaller, right? So when standard deviation is zero, means the service time, the processing time is constant all the way for all the flow units. Exactly the same number of seconds or milliseconds or minutes, exactly the same. No change at all. But that's very hard to achieve in reality. So in reality, when the standard deviation is very little, now again, how do we compare very little? Compare it with the relevant measure of the time. So if we see a sigma A, right, there is very little compared to the inter-arrival time, like less than 5%, less than 2%, right? Then it is as good as zero, right? Because in real life, we cannot see an exact zero. Every measurement will, you know, uh, give rise to some sort of a random noise, right? So that's why we need to be realistic. And same thing here, if we're measuring the service time, or in this case, processing time, same thing. As far as we're discussing queues are concerned, then the standard deviation will be like very little compared to the P itself. So if the processing time is 1 minute and your standard deviation is 0.05 minutes, then is very little, right? So like 5%, 2%, very little. Then you can might as well just say that it is zero. So now, when there are fluctuations, then Q must form. Must form. It's not a may form, maybe yes, maybe no thing. It must form. So very quickly, look at the bottom. When there is no standard deviation in the flow rate, right? In the flow rate means that it is what? It is no fluctuations in the flow rate. Means exactly every minute you will see two flow units coming in, spaced exactly apart in time. Okay, so that's like the time axis on the horizontal axis, and you see them spaced exactly apart because the spacing also describes the time gap. And in this case, the standard deviation is zero. Okay, so if your rate of processing at the server here is going to be, so if we have 2 per minute, we need to be at least 30 seconds or shorter our processing, right? So that we don't jam up. So if you are able to have also zero standard deviation in the processing time, right? Every time you process, you take exactly 30 seconds. No, I mean, you are like working up to your neck or forehead already at the server. Uh, the moment you finish, the next one comes along. You don't have any second to rest. Then it's okay, right? Yeah, because it's like clockwork, right? Exactly when one teeth of the gear leaves, the other teeth comes in, right? So it's like clockwork. Uh, will the queue form? No, because you can tune this up to 2 million per minute, and your server now is able to handle 2 million per minute service rate. Instead of saying the service time, that means the processing time, we talk about the capacity. So 2 million per minute. Then again, there is no time to rest and the utilization is 100%, but no problem because the moment I finish one, the next one comes along, right? So as a machine, no problem. So if I tune to 20 million, 200 million, as you can imagine, totally no issue. So it is not about higher the flow rate, then the tendency for the queue will form. It's no, not that, right? So nothing to do with the exact value of the FR, but a lot to do with the standard deviation. That's what we are talking about. So that's why it is the first thing we have to talk about. Why do queues form, right? So standard deviation 0 and standard deviation for the processing time 0, no queue will form. Okay, but let's disturb the arrival process a little bit. So standard deviation for the server, 0. So the processing time is very exact, very, very exact. Every flow unit will be given exactly 30 seconds treatment. So here, the first one is a little bit late because standard deviation is now is 0.3 minutes. Right, what goes down must go up again. So if you are a bit late, the next one better be a bit early, and the next one is very early, but it's too early, right? So it kind of averages up. And so the next one better be a bit late to make sure overall the average is still 2 per minute. That makes sense, right? And the moment there is a bit of the delay, the next one better be a bit ahead, a bit early to average it back to 2 per minute. So when you have this fluctuation and they keep coming, right? So let's just ignore these two flow units in the queue first. When the first dough arrives, we're still making bread. Uh, our server takes 30 seconds, right? But it was a bit late. It was a bit late. So that's fine, assuming there's no previous flow unit. Then the server will just start a bit later, right? And then this flow unit arrives and the server starts the 30-second processing. Remember, the 30 seconds exact, no fluctuation. Then it needs 30 seconds. That means all the way up to here if we draw it in the flow units time series. So it has to be 30 seconds. That means here. But before that, this flow unit would already have arrived right now. So while the server is holding on to the unit 1 here, the second in the last 5 seconds, 4, 3, so 6, 5, oh, second flow unit has arrived. 4, 3, 2, 1. But where is the second unit going to be placed at? It cannot be processed at the same time. So no choice. It will have to queue up. It will have to queue up. It will queue up no matter whether you allow it to queue up or not. That's why we say queue must form, right? The queue has to form because there is fluctuation. This is a must thing as we now gain understanding from the theory. So the second flow unit will be parked outside. Okay, so since we know queue will form, it would be good if we have a dedicated area where normally we'll call it the queue. We'll call it the queue, right? The queue formation area. Because we expect a queue to form. Just like going into a bank, you see those barriers, right? Those mobile barriers trying to form a path for the customers to queue up. So that's to indicate for the customers coming in, all not knowing each other, where should I stand? Oh, stand in line, right? Inside the queue formed up by the barriers. Why? Because the bank expects a queue to form. So if you expect queue to form, it would be good to have a arrangement for the area for those units waiting to be served to form a queue. Uh, But if you don't, because you say, well, I just don't give you the space, so you won't form a queue. No, sorry, right? You can't fight the physics. It will become randomly spread outside, like forming a hill, right? Because as there's more flow units pile up and the server is still busy, you will start forming a hill, right? A pile, a mountain of flow units on the outside of the server, and that's very unsightly, right? And of course, if the server itself cannot handle a mountain of flow units, then it may jam. It may have various problems, right? And so that is bad. And of course, if the server is a human and these flow units are humans, then we have even bigger problem, right? They might fight. They might say, "I was here first. Why are you, jutting in?" Right? No, no, no. I was here. It's just that I stepped away for a while to talk to my talk in my mobile phone, and so there will be fight, there will be social unrest, and police will come. So if you're running a bakery shop and a bank and whatnot, it's going to disrupt your business. So it is inevitable. So you cannot just close your eyes, don't form a, don't have a area for queue, then queue will go away. No, right? So queues will form. Now we have been talking about just sigma A being greater than 0. Already queue forms. What if sigma A is 0, but server has fluctuating service times, processing times? Then we'll see sigma P greater than 0, right? So our earlier two examples, we were assuming server has 0 standard deviation for processing times. So it's always exactly 30 seconds. But right now, we will come back to the first example. The flow units are exactly 30 seconds spaced apart, but service time, the processing time for each flow unit, fluctuates. Sometimes 25 seconds, sometimes 35 seconds, right? So on average, it is 30 seconds, but it fluctuates. So what happens? When the first flow unit arrives, it enters into the processing time, right? So it will take, for example, 35 seconds. So 30 seconds later, the second flow unit arrives. And what happens? It expects to be processed, but because it is an old machine for various reasons, yeah, for old machines, or it's a new machine, but it wasn't properly configured, right? Because the supervisor never thoroughly read through the 100-page manual, and so just start it and run and go off for coffee, right? It may be a brand new machine, high performance machine, but it wasn't installed properly. So there's one leg that's kind of like slanted to one side, and when it really starts operation, it starts to experience jittery kind of vibrations, and resulting in some service times being 35 seconds and 25 seconds. And I'm just quoting various very realistic, um, maybe unplanned, but maybe accidental kind of reasons why the service time might fluctuate. So the second flow unit arrives only to discover that the first flow unit still has 5 more seconds of processing time. So it will queue outside, right? It will have to queue outside, maybe for a brief moment, but queue has formed. That's why it is the first question we want to answer. Why do queues form, right? It is not due to high FR or low FR. And even at 2 per minute, you can form a queue. Even at 0.2 per minute, you can still form a queue if either sigma A or sigma P, either one of them is greater than 0. And worse, if both of them are greater than 0. So the bigger the standard deviations of either one or combined, the worse it is. That means the queue will tend to be even longer, more visible, and all that. So that is to be kept in mind all the time. And that's why in what follows, in some of the formulas, it is inevitable that we have to, or the formula will include these two parameters, sigma A, sigma P. No, there's no running away. Okay, it has to form. Now, here we see that the distribution, the histogram, think of distribution as the histogram. The distribution of FR will show very clearly, all right? Histograms are very nice statistical tool, almost like an X-ray to look into the bones, right? The histogram is able to look into the frequencies, something that our eyes are not very good at detecting. I mean, if you look from far, these two sequences on the conveyor belt might look similar, or we can't detect how much sigma is. Is it very severe or not? We can't tell. Not easily, especially when it's very minor. The standard deviation is very minor. We can't tell. So, but then when you plot a histogram, a zero standard deviation histogram will be just one stick, exactly on two. When you have small standard deviation, the wing starts to form. First, the wing will spread a little bit if the SD is small. If the SD is bigger, it starts to spread wider and wider. And ultimately, maybe it will be one bar here and then many, many small bars far, far away, possible. Or forming a bell curve or something like that. Now, very odd shape kind of a histogram, like lopsided to one side and all that, tends not to be observed in real life, right? In real life, it is due to uh, random factors. So it tends to be more or less on left and right. It may not be exactly symmetrical, but it's going to look something like that. There's some bars on the left, some bars on the right. Mainly, the majority is still on two, but there are occasional uh, smaller values and larger values. And this is true for FR and also for the service rate. Okay, so existence of Qs does not necessarily mean that sigma A is not zero or sigma P is not zero, right? So here we are just talking about some examples where Qs form not exactly just due to the sigma A being non-zero, sigma P being non-zero. How come? I thought you just said, or I just said, that Qs form only because of these reasons, these two parameters. Now we add some more. Why? Well, because this is true when we have steady state equilibrium status. That means the pipeline, the conveyor belt, the processing, the process is continuously in motion. All right. And you are performing, you are processing the flow units, and FR in equals to FR out. Right? That's the LED check for whether you have SSE or not. So when you do have SSE, then Qs must form when either one or both of the sigma A and sigma P are non-zero. So that's true. But, right, what's the but about? When we are not in SSE, so this part is talking about when we are not in SSE. When we are not in SSE, then you can have FR in way larger. That's the scenario of the layman's imagination, right? Way larger than FR out, so as to jam the machine. Yeah, because of course some servers or some processing or some resources, they have anti-jam ability, right? For example, if the resource is a human and you're seeing that mad crowd is coming, rushing to get free vouchers, then of course you will tell the security guard, can you quickly close the door, right? So let me finish up this batch of customers first. So when FR in is way larger than FR out in a sustained manner, so in a sustained manner, and if it jams the machine, then FR out is zero. So if it's a machine, then the machine is going to raise a red flag, red light, lights up, and it stops producing anything. So FR out becomes zero in a more permanent setting. Permanent doesn't mean until infinity, but permanent like it will not resume working until being fixed, right? So then you have, even if you now have FR in a very uniform manner so that the standard deviation is 0, you can still have Q formed because basically the machine has jammed, right? It has stopped working. Then in that case, you might say, well, my sigma A is 0, my sigma P is also 0 because it is producing at a 0 rate very consistently. So sigma P is actually technically 0. So then when does a Q still form? That is an exception because it is not SSE. Now there is high FR in, there's 0 FR out, and yes, sure, Q is formed and it will never shrink, right? Not because the resource is not clearing the queue, and this is an exceptional condition. But the outcome turns out to be the same as forming a queue, so it does answer our question: how come there's a queue, right? But that is technically a different situation. So I need your eyes to be now lightened up and be able to detect these two situations and not be roped into the false interpretation that hey, somewhat the theory is not very consistent, right? But it is, right? So make sure you are able to tell this apart from the SSE situation. Next, let's micro-examine and enter into the queue itself. From a theoretical perspective, what is the meaning of queue system or queue process, right? So we would say queue system. And I tend to want to use the word queue system to refer to the whole thing. What is the whole thing? If you didn't or couldn't recognize, there are three components in a queue. First and foremost is the boundary, and that's usually the um, least emphasized in textbook, because this boundary defines what is inside the queue system and what is outside the queue system. If you are inside, then you are part of these numbers that are counted and predicted by the formulas, whether it is count or timing. If you are outside the queue system, then you are not counted, you're not timed. And of course, in real life, if you are part of the queue in a hospital queue system, then you have the right to be impatient. Then you have the right to complain. How come I waited for 3 hours, right? My blood has dripped dry and still haven't seen the doctor, right? Yeah, so there's a material difference, right? And what gives you that permission, that I won't say right, but the authority or even to raise a complaint that you have waited for very long because you are inside the system. And then if you are not, if you're just loitering, you know, around the garden in hospital, enjoying the freshness, all right, of the greens and the flowers, you're not part of the queue. You're not waiting to see a doctor, right? So you don't have a right to complain and say, why am I waiting for so long? You don't. Right? So the boundary, therefore, now using that hospital's analogy, now gives you some sense that being physically inside the hospital doesn't mean you are part of the queue system, correct? Yeah. Being even if you pretend to queue up, these days we hold the ticket number, right? So people don't really queue up. But even if you pretend to queue up, that also doesn't give you the right because you are not in the digital queue. You don't have that ticket number. And so you can't complain and say, how come I stood here for so long and nobody attends to me? You cannot do that. Sorry, sir, please take a ticket number and we'll come to you when your number is up. No, so if it's based on digital ticketing, then these queue up customers or flow units will be part of the digital queue inside the memory of the server of the hospital. So it's invisible, right? So uh, and that's a good illustration that physically queuing up, like in the old days, you are first means you queue up, you stood there earlier than others who arrived later. and modern days where you take ticket and you don't have to physically strain yourself by standing there for 3 hours just to occupy the position. Um, that distinction, right, all the more illustrates that queue process is quite well described by the theoretical three components: the boundary, and the other two are obvious, the queue itself. So when we say queue, we're talking about this part. And then the servicing station, right? The servers area, where here we can see 4 servers. And the yellow dots, orange dots, they represent the flow unit. In the hospital example, the blue stations here could be triage stations, where the nurse might first, pre-examine you, your weight, your height, your heart rate, blood pressure, right? So those take a bit of time, 5 minutes, 10 minutes, and there are 4 such stations, and they are currently all busy. They are currently all serving, each serving one customer. So these 3 components, again, quickly: boundary, queue itself, and the servicing stations. Right? And the way it goes is, or the theory looks at it this way: flow rate comes in, and in the now look, historically there are 2 uh, groups of scholars looking at the same physical phenomenon known as queue system here. The operations guys will look at it and call it the flow rate, right? Flow rate. And FR is the typical notation. FR, that's it, flow rate. The stochastic process people, the queue system theory people, will look at it as inflow, and the typical symbol is lambda. So I want to tell you that they are the same. So FR equals to lambda. Okay, there is no modification. They are just different terminologies, different symbols attached to the same physical phenomenon. So the higher the flow rate, the heavier the traffic. Same as the higher the lambda, the heavier the traffic, the inflow. And then of course we have we have the FR out. The FR out in steady state, we say it is the same as FR in. And so here we will not invent another symbol, lambda in, lambda out, and we just call it lambda, because all the calculations, all the Little's law, right, all the formulas that we see in queue process, they only work when there is steady state. They only work when there is steady state. So might as well we just say the inflow is lambda, the outflow is also lambda. Okay. So despite the inflow, the flow units coming in, having to queue up potentially, and then being served maybe randomly by any selected triage stations, eventually it will come out steadily as lambda if we have steady state. So another terminology difference which we have encountered before, the operations people will call the time spent by the resource to value add the flow unit as processing time, because in a manufacturing setting, it's adding value to the bread or the sardine can or whatnot. But the queue theory folks will look at the processing time P as service time. They will call it service time. And actually, they also use another Greek letter called mu to denote service time. So if you do see mu in a queuing theory setting, that talks about queue, then you should not think of it as the statistics population mean symbol, because that is also very commonly used in statistics textbook. Yeah, mu refers to the population mean of anything, and queue system theory uses mu exclusively for the for the service rate. So mu refers to the service rate. That means number of customers processed per minute, per hour, and therefore the service time is given by 1 over mu. Again, don't confuse P and mu, right? So P and 1 over mu, they are the same thing. They are the same thing. Okay, so just like um, our A inter-arrival time is 1 over lambda, the same thing, inter-arrival time. The time gap between two consecutive customers, right? So on average, the inter-arrival time is just the reciprocal of the flow rate, right? So we just need to get familiar with, or very, very fluent with the two dialects, right? One is coined by the operations people, the other one is used by the queue system people. Okay, so the three components, what's so special about them? What do we care? We care about counting and we care about timing. We care about counting, we care about timing. So just so you understand what we are looking at. We care about counting. Why? Because if we do the calculations and we realize that IQ, that means the queue size, that means counting exclusively the queue size, is going to be 320 on average. Then don't pretend that the queue will not be running up to 300 plus people or 300 plus vehicle or 300 plus flow units, because already theory predicts on average. That means there can be more. Momentarily it can be 350, but sometimes it could be 280. You kind of average it down to 320. So if the calculation shows some finite number, that is the average, and it's always the average that the formulas calculate, right? Remember Little's law? Yeah. So Little's law, we wrap a Little's law boundary here, and then we say what is the flow time through this Little's law boundary, and what is the flow rate in. The flow rate in, the FR, is lambda. The time it takes for a customer to wait, you first join and then start timing you until you exit, right? So that's, we just call it TQ first because we're going to talk about this quantity. So the time in Q, TQ, is the flow time through the Little's law boundary like this. Make sense? Okay, so by Little's law, the average number of customers inside this Little's law boundary is going to be lambda times TQ. That's just simple application of Little's law. And same thing, if I wrap a Little's law boundary around the servicing station, first of all, at steady state, the FR is just the same as lambda, yeah, because it's like water flow through a hose. When the water is flowing continuously, we call it the steady state, right? From in to out, there's constantly water coming out from the hose. Then the water flow rate at any segment of the hose should be on average the same, because in equals out, water cannot accumulate to form a block somewhere in the hose, right now, yeah. So or suddenly the hose is squeezed because water drained out quicker, faster than the water coming into that particular weird spot of the hose. Very, very, unimaginable. So the FR in is lambda, and the time spent for the customer to go out, time, not physical space, the time spent for the customer to come out from this servicing station is the service time itself. Because if the nurse takes long time, right, then that's the time spent there. But if you are very quick, you already have your weight and height measured, and the nurse accepts it, right? Just a quick heart rate and blood pressure measurement, then you're out. Then that's the time. So it's P itself, right? So it's just FR times FT. Notice that? That's again reapplying Little's law through this boundary. And notice something here, that I was just looking at the first servicing station, but it can be that we have 400 servicing stations, and the answer is the same. Right now, yeah, so it's just lambda times the processing time. That's it. That's it, right? And that is not wrong. That's not wrong, because you can have many servicing stations, but if you have very few customers coming in, then there shouldn't be a lot of customers occupying all the 400 servicing stations, right? Now, yeah, so it shouldn't be dependent on how many servicing stations you have. And then for the entire system, the inventory is the WIP from Little's Law's perspective. But in our hospital example, that will be the number of customers. So if the question asks, in total, how many customers are there in the hospital? That means including the queue area and the servicing station. Then you just add up the averages to give a average total. Okay, so we just combine the math and that's it. Very simple. And for processing time, we can do the simple Little's law because the service time P is simply 1 over mu, right? So lambda times P is lambda over mu. For IQ, we need to know TQ first, then we can apply Little's law. Okay, what about flow time? Flow time. Time is also very important, especially when you're dealing with human customers. So for many retail businesses, and even in this hospital setting, you have public customers, right? If your time in queue is very long, you already know that because theory, the formula tells you so, or the overall flow time is very large or larger than competitors, then it is going to be causing pain, right, to the especially to human customers. I say especially because it is not the case that if it is a manufacturing setting, your flow units are basically non-human, right? Then it's okay. But remember, for example, I'm just quoting a very a drastic example. If you are manufacturing food, right, and suppose you're doing tofu, yeah, the very soft bean curd, and it gets contaminated easily, it gets oxidized very quickly, right? If you're exposed in a prolonged fashion in the factory, then you're going to produce sour bean curd, right, instead of fresh, tasty bean curd. So you don't want the bean curd to be waiting. If your TQ is like 3 hours, that means the bean curd, every bean curd on average has to wait for 3 hours before it gets packaged. Then you are in trouble right now. Your bean curd tends to have low QC, quality check, and tends not to make it. And so the yield will be very low. You'll be losing a lot of money. So again, TQ is very important, but very, very important when it comes to retail and human customers. And of course, service time is another time that adds to the total time, right? Typically, when we queue up, and by the time it's our turn, we are kind of happy, take our own sweet time, right? But you also don't want 3 times, 5 times the usual processing time to handle your transaction. So, for example, if we stand in line in the bank, thankfully these days we don't spend so much time in the bank. In the older days, to go to the bank is probably a half-day leave scenario. I better apply for afternoon half-day leave, right? Because if I go to the bank, there may be long queues and I have to stand in line, and that affair might take 2-3 hours. And so, in order not to upset my boss, I better apply for half-day leave. These days, right, if you stand in line, if you do have to go to the bank because it's a complex transaction, then you go to the bank, you stand in line, and let's say you wait for an hour, which is kind of very long already, right, in today's standard. And then you finally get your turn to meet the bank officer to discuss your complicated transaction, like opening a trading account while using your investment linked product or whatnot, and so on and so forth. Right? Okay, fine. But your intention, your plan is to kind of quickly finish what you intend to do with the bank, and then that's it, right? So while after waiting 1 hour, it is your turn. Okay, you feel good. But what if the bank officer right, keeps asking you to, can I verify your identity? Oh, no, looking is not enough. Can you please fill in this form first? We will check first, and then I thought I've given you my ATM card and you can get all the details in there, right? No, sorry, procedure wise, you have to do this. Okay, fine, you do that. A little bit not happy. And then after that, you have to open a trading account and you have to refill in again the same details, right? Your name, your passport number, your address. I thought the bank can just easily copy over, right? But no, they want you to fill the form. So imagine that kind of repetitions and delays. Are you going to be happy? Even though you're currently being served, right? You're not going to be very happy about it. How come your procedure is so backward? How come you keep asking me the same thing, right? So now your processing time went from an average of 10 minutes P to 30 minutes or 50 minutes. Are you going to be happy? No. So retail customers, again, very sensitive to TQ, very sensitive to P. And so, I mean, much more sensitive to TQ than P, but again, don't let P extend arbitrarily, right? So therefore, the flow time through the system, the flow time through the hospital, through the bank, right? You want it to be, I mean, if you are a very proactive system administrator for the hospital, you want to look at these parameters and say, how do I plan for a shorter flow time for better experience for my hospital's patients, right? I mean, imagine spending 3 hours in the hospital. Most of the time looking for where's the department that I should go to, waiting, taking ticket, wait again, right, to see the doctor or see the triage, take take the ticket, or wait again to see the doctor, take the ticket, wait again to see the pharmacist. And by the time you come out, it's like 4 hours later, you're so tired, right? So that would be the kind of experience if you don't care about tea. Now, same thing, going to the bank, right? Imagine taking a ticket to uh, wait in line, right? After 2.5 hours, then you uh, get to see, I mean, it's your turn, but the bank officer says, can you just give me 5 minutes? Let me do my quick checks. Then disappear for 5 minutes. Come back, ask you to fill this form and then, it's another 15 minutes. By the time you come out, half your afternoon is gone, right? And it's just so frustrating and time wasting from your part as a customer. So if you are, in your career becoming someone who has the authority, then better use your ability, right, to exercise some of these queuing theory knowledge to look out for the count and the timing. This third slide here, just some terminologies gathered together that I have actually mentioned or used them. And here is the sort of dictionary of the terms. So queue process is the picture I showed you, the three components: boundary, queue, service station. And so from the theoretical perspective, that's it. Customers may loiter around, move around the queue system in the bank, in the hospital, but from the queuing theory perspective, they don't matter. You are either queuing, or as a customer, you are either queuing or you are in the servicing station. You are either waiting outside or you are meeting the nurse in the triage. So you can go to the toilet, you can go to the canteen, you can have coffee first, but all the time you are waiting, right? So queuing theory doesn't look at all these things, and that's why it's very widely applicable. It can go from a factory in Tuas to um, the queue process in Sengkang Hospital. It doesn't matter, right? No problem at all. Okay, servicing station can have one and obviously more servers. Our example just now, 4 servers, right? Queue only has customers. Customers only has 2 states in the queue system. You are either, yes, waiting or being served, right? Because you're either in the queue or in the servicing station. And after that, you flash out. You may have small talk with the nurse. Hi, thank you so much, nurse. You look very nice today. I wish you a pleasant day. And all these talks, part of the service time. Sorry. Okay, so that's part of the service time. Then you say bye bye and you exit and you flash out. Okay, so there is no third state for the customers. Servers or the triage stations or the resource also have only two states. Either you are busy or you are idle. Some students um, use the wrong term and they describe the server as waiting for the customers to come in. Not wrong from a layman's perspective, but then from the queue theory perspective, we don't say that the server is waiting. We reserve the word waiting for customers only. So customers only either wait or being served. Servers are either busy or idle. Okay, so keep that in mind. Then we have the time in queue. Where's my cursor? Okay. Okay, so we have the time in queue itself, which is TQ, right? So it represents the flow time through the queue. The flow time through the queue itself, TQ. This is, so far up to now, still a black box, mysterious notation, because we're going to spend a bit of time to talk about the formula for TQ, right? This is like the genesis, is the contribution of the theory to give us TQ. Once we have TQ, we can apply Little's law for various other estimations, right? So this is the most important part. Also, this time in queue is on an average out basis. So if you do imagine that, hey, wait, the first few customers coming in to the hospital, at 8 o'clock in the morning when the hospital opens, they don't wait. There's zero TQ, right? Wait, this TQ, first of all, only runs or only works when you have steady state. So when the hospital just opens up in the morning, when there's no one in the system, right? So obviously, yes, the instantaneous TQ is zero, but that is not the average TQ, not this TQ that the formula predicts. So when you do have steady state, the first few customers enter, saw the doctor, saw the pharmacist, comes out, right? Then you have people going in, and there are also moments when the queue is empty or having only one customer, so that the time in queue for one or two of the customers are very short, right? Then you say, but then isn't that wrong here, right? When TQ says it's 40 minutes. Again, this TQ is on an average out basis, average out over many customers. That's right? So the first few might have very short TQ, 3 minutes, 5 minutes, but the last few might be 1.5 hours, 1 hour and 20 minutes, 1 hour and 15 minutes. So if you average them up, it's kind of right, 35 minutes to 40 minutes. Yeah, so that's the whole idea, okay? Arrival rate. We talked about it as flow rate. Remember the clash of the titans, right? So the operations guys and the stochastic guys, the queue system guys, they have different nomenclature and the symbols for the same physical phenomena. So flow rate becomes arrival rate. FR becomes lambda. Service rate becomes, or rather the capacity of server resource, right? The CML becomes our service rate. Now it's called service rate. CML that we learned in the last few sessions becomes mu. Flow time of the system. We saw this formula just now, right? That's what we said. Inter-arrival time is the reciprocal of arrival rate, calculation-wise. But the meaning-wise is the time gap between two consecutive customers. So the thinking-wise, the understanding is whenever not the first, but any customer that comes into the hospital, we start the stopwatch. We keep it running until the next customer arrives. And that duration is our inter-arrival time. Of course, if that is not fully reliable, we repeat that for several more or many more consecutive customers, and then we have many inter-arrival times, the instantaneous inter-arrival times. We average them up, then and only then do we get an A here. So we don't take the any single randomly chosen interarrival time, which will fluctuate, right, from customer pair to customer pairs. So we take the average, and it should be a constant. Next is service time. Service time is what we call processing time earlier on, right? And that is the reciprocal of CML. P is equal to 1 over CML. So same thing here. P is equal to 1 over mu. Okay. So we call the flow unit FUN, but in the queuing theory speak, flow units are called customers, regardless of whether you are human or inanimate object. They're all called customers. And resources are called servers. I think you figured that out by now, right? So it's not difficult, but anything is a customer. Okay? So a sardine can waiting to be processed is a customer, right? But more because the stochastic processes and all that, they were developed with the idea of people coming in randomly, being served, all right? What will be the situation like? How long do they have to wait, right? So you have to answer that question. So the terminology is appropriate then, and then you can extend it, right, to inanimate objects. Unstable queue and stable queue. There's a litmus test mathematically. So if lambda is less than mu times the number of servers, mu is the resource capacity. So that means one triage. One triage can handle 4 customers per hour, let's say. We have 4 triages. Then collectively, you can handle 16 customers per hour. Correct or not? Yeah. So that's the whole idea. And can we let 15 customers per hour traffic come in? Sure, because we still have stable queue, right? So that's okay. Nice. And equivalently, we are saying that the inter-arrival time, the time gap between consecutive customers, better be large enough, larger than the service time or processing time needed to handle each incoming patient. Does that make sense? As the server is spending time, the P here, right? The time gap better be large enough for the P to finish, right, before the next customer arrives. So it makes perfect sense. And you notice here that the M disappears. Doesn't matter, right, how many triage stations you have, how many servers you have. All the servers are operating on their respective customers, their respective patients concurrently. So you just look at one station, right? So in this case, the M disappears, and it is true physically that so long as the next customer arrives with a time gap that is on average longer than the service time needed, average time needed to process or handle one patient at any of the triage, then it's fine. That's okay, because any of the freed up triage can then process the next incoming customer. Huh? And if you fail to satisfy this inequality, then you are said to be in a or having a unstable queue. So what is an unstable queue? First of all, it implies that we don't have SSE. And what's the consequence of that? Cannot use all the formulas, including Little's law. All fail, right? Number 2, it also means that when you have unstable queue, the longer you operate, the longer is the queue part of the queue system. So the longer you operate, because lambda is larger than your combined servicing station's ability to clear the customers, every hour you accumulate lambda minus mu m average customers in the queue. So that means the bigger the difference between lambda and mu m, the quicker your queue will grow as time passes. The more unstable it is, in other words, right? So unstable queue theoretically just means whenever lambda is on an average out basis. Now this is also important. Not that the one moment, right, the instantaneous moment that lambda for a brief moment is larger than mu m, But then later on, it's like half or 1/3 of UM only, right? To average it down, that doesn't count, right? The momentary uh, uh, satisfaction of this unstable Q inequality momentarily, right, for a short while, is not actually satisfying this inequality. Why? Because that's lambda instantaneous. This is lambda itself. Lambda itself means you measure arrival rate for a long, long time, and the average out arrival rate actually did not exceed mu m. So that's why you're still having a stable Q environment. Now, of course, when government or even private funds, they are planning to build a hospital, you want to talk about capacity. Actually, how many patients per hour are we planning to handle? Because that has a lot of implications on, your the size of your hospital, the arrangement, the hallway, yeah, even to the maybe the size of your lobby and your front gate, yeah, because what kind of scale of hospital are we planning? Are we designing? Are we building? And that is the first and foremost question right now. Yeah, of course, then we to answer that, we do other research and data measurements, like the demographic profile of the residents here and so on and so forth. And then you want to build enough stations, your mu m, right? Because once you have determined lambda, oh, we're going to build this hospital for this precinct here, and this precinct is very dense, lambda is expected to be this and that. So it's a separate study, right? So our hospital should be able to handle lambda plus a little bit of buffer. And so our mu m better be how large. And so you then can handle and gradually plan out the right design so that you don't end up after 3-4 years of building up the hospital, realize that your hospital is always overcrowded. Always overcrowded. How come the planner never foresee this upfront, or it's super underutilized? The hospital is so huge, and hardly you can see anyone in the hallway, right? So and it's not due to service not good, but then it's like too huge a capacity, and it wasn't meant to handle the right lambda. Okay, so that is for hospital, but the same idea goes for many other settings. Singapore is planning a Terminal 5 for the Changi Airport. Is there big enough lambda? Right, so maybe from the planner size, in the next 10 years, lambda is expected to grow and grow and grow. Well, we didn't expect the tariff war to start so early, right? But let's say that it's not affected by tariff war, and so lambda is going to grow and grow, and our existing 4 terminals will not be able to handle. So actually 3 terminals, right? So 4 plus 5, right? So the 5th terminal is going to build, and it will increase mu m to be more than 50% of the expected lambda in 10 years time. So no problem, if we able to serve Singapore for another 15 years, example. So all these are very important planning parameters, because how else are you going to be able to convince, not to say your management and the funding ministries, but yourself? How do you convince yourself that this is a proud design, right, that can handle the traffic? So all these are meant for you to apply into the scenario to make better decisions. That's all I have to say for now for this topic. Thank you, and see you in the next video.